And then I should share screen. Okay. Then I can do that. And do this. Right, cool. So let's get going. So today we are going to talk about probabilistic numerics, and the aim of today's lecture is that it's going to be a little bit more, a little bit less exact, if I ever was exact, precise. What I'm going to try and do here is to raise our view a little bit what you can actually do with statistical learning, right? So we're going to look at that, and hopefully you can see that we've really done something quite general with the methods that we looked at. So to begin with, I'm going to show this thing, right? So Neil put this up very early, of saying that we got some data, we have some model, and what we're going to do is we're going to do some predictions. And to go from these two things, we add some compute, right? That's the thing. That's the process that we get to from there. What we're going to look at, or what we have looked at, is that this started off already with talking about the example of certain, right? Where basically the notion was that Giuseppe Piazzi did actually measure these things exactly correct, right? So there was an error in these measurements. That led Gauss to actually do that prediction, right? By assuming there's a noise, by assuming some ignorance of where the planet actually was at the specific date. Then we moved on and we did like first the linear systems, and then we did Gaussian processes, where we said, you know what, I think the model is kind of this, but I'm a little bit ignorant or uncertain about it. So we added uncertainty about this, right? We took those two things. And then our computation so far has always been analytical and exact, right? We've used these conjugate models where we just derive everything exactly, and it's, if there's anyone's fault, well, it's your fault, or actually my fault, because I did some errors in the worksheets to get the math correct, right? However, in many cases, we also have uncertainty in the computation, right? Now we've got three sources of uncertainty that are mixed together in our prediction. And today we're going to look at uncertainty over computations. So just to continue this, what do we do with uncertainty, right? So the first thing we looked at was that when we had, well, we can take this example, where we had this model uncertainty, right? So in this case, we had some form of ignorance that we parameterized over our function space or over our hypothesis space, and we integrated this out, and then we reached a posterior to do a prediction, right? Then last time, we looked at the Bayesian optimization setting, where we used the uncertainty to make decisions, right? We said that actually the role of uncertainty, which it actually is in the first case as well, but it pops out clear in this case, is really to make decisions, right? Because what we were interested in was the learning, right? And you learn something that you don't know. And if you haven't parameterized what you don't know, and ideally the degree of how much you don't know it, it's really hard to actually do any form of efficient learning, right? So actually, what we do with uncertainty, the way we can think about it, right, is that the uncertainty is something that we have so that we can go out and address it, right? Right, that's the key thing. So really, it should really be thought of as whatever quantification that you have for decision making, right? In the end, you have to make a decision, right? Then the uncertainty might not be something that you actually use for prediction, but coming up to that, it's very, very important. So I wanted to then extend this notion of quantification of uncertainty. So we talked about this thing last time where I put two things where I said aleatoric or stochastic uncertainty. I always confuse these two because they're very nice sounding names, so I confuse them. But aleatoric uncertainty is then the randomness that's inherent to a system or noise in your measurements. These are things, it doesn't matter how many times I weigh myself, if my scale is just going to report an error. I'm not going to get clearer how much I weigh, right? Then you have the epistemic uncertainty, which was the one we worked with last time, which is uncertainty related to our ignorance of the underlying system. This was the one in the base of the example where we didn't actually have any noise in any of the examples that I showed. Then this was the one that we tried to make decisions about to address, right? And now then, we're adding this. We're adding the notion of computational uncertainty. So this is something that you can think of related to as possibly finite computations. So I just run something for a set amount of time and then I stop, right? Or something that's intractable. It's something that I cannot compute. And now I do some approximation of it. And now I get uncertainty due to that. Cool. So I'm going to show a quote, a very long quote from Cockay, who said this. This contains two really important things that I think we addressed a lot in this course. The need for probability only arises out of uncertainty. It has no place if we're certain that we know all aspects of a problem. But our lack of knowledge must also must not be complete. Otherwise, we would have nothing to evaluate. This is the first point, right? Where I said, if you don't know anything at all, right, you cannot really learn. It's really, really tricky to do this, right? But as soon as you know something, right, then we can see the effect of that knowledge and we can update it through data. But if we don't have our prior, this is effectively the free lunch, right? No free lunch. If we don't have anything, you can get anything else, right? But if as soon as you have something, you can relate back to that. There's thus a spectrum of degrees of uncertainty. While the probability for the 6th decimal digit of a number in a table of logarithms to equal 6 is 1/10 a priori, in reality, all aspects of the corresponding problem are well determined. And if we wanted to make the effort, we could find out its exact value. The same holds for interpolation or for the integration methods of codes or gaps. So this is 1896, and already at that point, Cockay is talking about the notion of uncertainty in computation, right? Because this is the last statement, right? Okay, cool. So, the reason why we want to do this is computation is usually really, really expensive. So, what we would want to know, if we had uncertainty about this, what we could say is, if I run this 10 minutes more, if I spend this much money on AWS to do this, how much knowledge could I possibly gain from this? Right? That's a really, really strong statement that we would want to be able to do. You can also think in the base offsetting, if you remember in the beginning when we were just doing random search of things, or just using the mean, we didn't use our uncertainty at all. We couldn't really quantify how we should do things, right? In which order we should pick it up. When we included our uncertainty, we got this explore exploit thing that popped up, right? So what should I compute in order to reduce my uncertainty as much as possible about the problem, right? That would be a really strong statement, right? If you've got a choice, you should do the thing that you learn the most from, right? And then if you have gotten the result of the computation, how much should you trust the computation that you've done, right? And finally, we're not, most machine learning methods, slots, you make a decision, it goes into another decision, blah, 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 so forth, right? So it's a chain of things. And of course, no chain is stronger than its weakest link. So why should you, if you spend an awful amount of effort here and very little here, you probably wasted most of the time you spent over here, right? So actually, taking in the uncertainty in the computation, you might have derived the most complicated, super good model that you can, but then you did an awful computation of it, right? That now is actually going to give you awful uncertainties going down very likely, coming from the computation. So you want to feed that along, right? Cool. So we're going to then follow compare or care. And think about what are then things, if you have the notion that anything I can have some belief in, I can do statistical inference in. So what do I believe in? Well, I believe in functions at the moment. I also believe that Bristol City will win on Saturday, but that is very, very high for certain. But what we've done here, right, so far, we've modeled functions, and we looked at minima for functions. What are more interesting things that you can do with a function, right? What we're going to think about is that a function can have something which we refer to as the quantity of interest, right? Could be its minima, could be its integral, could be all sorts of things that we can extract from the function, right? We've done the most extreme of saying, there's some function, I want to learn it, right? But actually, in most cases, what we're interested in is extracting something from the function, right? The base of case, it was the minimum, right? So we're going to try and generalize this. This here is not a graphical model, okay? This is just arrows and circles that are somehow connected, and it's a much more abstract notion. Don't think about it as a joint distribution of anything, right? What I'm going to try and say here is that we have some form of joint distribution of everything, right? Then I have a quantity of interest that I'm interested in, right? So this here is all the x and y values, combine the joint distribution of them, how it works in the world. I'm interested in doing regression. What I'm interested in is finding a conditional distribution that tells me if I know an x, give me the distribution of y, right? Cool. So now what I'm going to say is that if I knew that full joint distribution of everything, it's just math to get to there, right? So I'm going to say that this here, and hat, is the quantity of interest. This here is the underlying knowledge of everything. And this F here is the quantity of interest operator. See how abstract we're going to be now, okay? Now, in most cases, right, because we're doing machine learning and not just math, we don't have access to the joint distribution. What we do have access to, remember, we've got access to a finite sample set of the joint distribution. What we do is then we design really, really clever algorithms, that tries to go from this finite sample set and take us to this quantity of interest, right? What we most often do, and this is a bit of a criticism, what we most often do in machine learning is that we do this, okay? We say that I don't have this thing, it's latent. What I'm going to do is that I'm going to try and take my finite sample set, and I'm going to try to, from that, learn everything. I'm going to try and approximate the underlying joint distribution of everything. And if I do that, then I can just apply the same operator of interest, right? If I do that, I've learned everything, and then I can get it. We should have a little bit of criticism towards this, because let's say, let's go back and think of the base of the example. If I'm interested, let's say now this is the minima, and that there is an underlying unknown function. Why would you ever learn the function to find the minima? Well, sure, if you learn the function, you can find the minima. It's one of its characteristics. But this is a bit of overkill, right? Actually, all functions that have the same minima are equivalent under this, right? And all the points that are really high, we don't care about, right? And that's what we did with the acquisition function in base of. We did this thing where we picked points to effectively try and learn better at points that were good, right? So, what we really would want to think about, this is a more sensible setting, essentially, is we want to design directly algorithms that goes to the quantity of interest. But then we also are in the active learning setting, where exactly like base of, we have an operator S that is the thing that queries the underlying unknown thing and gives us the sample set that we apply our algorithm. So exactly like base of, right? You can think about this as S is your acquisition function, right? This A that we had was kind of trivial, right? If you looked at the example, we just took the minima of the points, the finite number of points I've seen. That was it, right? And we had this model that we used for the acquisition function of fitting this Gaussian process. Okay? So that's the setting that we're going to talk about today. So I've just generalized the concept. We can now think about this as the integral, the minima, whatever this thing is here. It's a quantity that can be extracted from the function. We want to be a bit clever so that we just don't learn the function and then extract the quantity. We want to do this in a more clever way. Cool. So, is there any questions on this now? No? It makes sense? Kind of? Good. So the quantity of interest that we're going to talk about specifically today is the integral of a function, right? Okay. So now another statement, I just think this one's quite funny. Integration is a scientific numerical problem in many fields of science and engineering. It's a key step in inference where it is encountered when averaging over the many states of the world consistent with observed data. Indeed, a provocative Bayesian view is that integration is the single challenge separating us from systems that fully automate statistics. More speculatively still, such systems may even exhibit artificial intelligence. Right? I hate that word artificial intelligence, but we kind of have to use it somehow. And this points out kind of a funny thing about this. I don't think we'll solve integration, so therefore we'll never reach AI. So happy, joy. Cool. So this statement here comes from a book that has been very recently released on this topic. So what do we do when we do integration, right? So integration over some function, in this case, is that we take an infinite sum over some measure, right? The normal thing that we've seen is when this d nu of x is just the canonical measure that you split up when you see a Riemann integral, right? You take a box, so each part of x is equally important, and then you sum them up, right? But it's important that we think about this as a measure, right? dx is a measure, and we can alter that measure, and that's what we're going to do, right? Just to give you a little bit, I showed this before, but if you think about marginalization, and this is exactly what they were talking about in the previous comment, what you can look at when we split up our parameter space from d theta, we push it through our prior assumption, P of theta, you can think about that itself as a new measure. It's the measure that respects your knowledge, and then you average this. Right? You can think about it like this: the areas that you believe in a lot, you make really big, they count more, right? That's effectively use marginalization. Cool. So let's think about a very simple way of computing the integral. I'm going to take the information operator S, that's just going to take my space, and it's going to chop it up in delta x bits. Then I can design an algorithm. Here is the simple trapezoid rule, right? I take the average of the 2 points, I take delta x, and I sum them up, right? Really, really simple. So what's a little bit annoying with this, with what we've done so far? Why is this why doesn't this feel like a very nice thing to do? What is it that we're not taking into account? Yes?
It's an approximation.
It's definitely an approximation. It's absolutely true. And what would you do when you pick an approximation? What makes an approximation good? Or how can you determine if an approximation is good?
If it minimizes the uncertainty or the error that it has somehow.
Exactly. Where does this uncertainty come from? Well, how can I get a grasp of this uncertainty?
The delta x. If it's smaller, then the error should be smaller.
Absolutely. This here, right? If I take that to the limit and I just sample absolutely everywhere, I will get the true value, right? But let's be a bit, you're very mathematical. I like it. You're thinking about this from a very mathematical point of view. I want to be a bit dirty machine learning, right? So one thing, it seems like this algorithm here is independent of F. Right? Doesn't it seem a bit weird that you approach the problem in exactly the same way, independent of what you're integrating? Right? Thinking about how we thought about knowledge, right? We always said that if you want to learn something, you should take all the stuff that you know about the problem, try and chuck that in so that you can learn more efficiently. Now you make that jump to computation, right? If I want to compute some quantity of interest about something, if I know lots of things, so for example, say that I know this function is 0 from -infinity to 10, what should I really use split up the space uniformly? It feels a little bit odd, right? So what we want to do is that we want to take in, this is where we make this a machine learning problem. We want to take in the knowledge that we have about the function in order to do the right computation, right? Let me give you just a silly example of this, right? Or, no, I have this slide first. Let's think about this. A numerical method is something that estimates a function's latent property given the result of computation. Right? That's the definition of a numerical method. Then let's read the bottom one. Statistical inference takes data in the form of measurement of observed variables and aims to return predictions of the quantity of interest. Numerical algorithms does exactly the same, but instead of being measurements of observed variables, the measurements here are evaluations of some computation. So some result I get out. Right? So the notion then is, should we think about this? Should we think about computation? Should we go back to the previous graph and try and say, can we put our knowledge about the function into this? And then we can treat this as a statistical learning problem. Exactly the same way, because actually, what's the difference, right? The only difference is here, right? Cool. So, just to give a hint then on what we're going to do, or one of the things that we can do. Right? So here I got this function that we're going to look at. This function doesn't actually have a closed form integral. The integral is really, really easy to evaluate. It's a very simple function. Now, here's one quadrature. I've decided to put the boxes in that way. Here's another one, right? These two will give completely different results, right? What I would want is to come up with a way of using my knowledge about the function and then to be able to put these ones here in order to reduce the uncertainty as much as possible, right? That would be the thing, which is exactly the same thing as base odds, right? Then we're just looking for something else. Cool. So, if we could parameterize that notion of uncertainty of the output of the algorithm, we can now choose which algorithm I should use, right? I know this is the function, so therefore I should probably use this algorithm. It's really good for that, right? I can make much more efficient use of expensive functions. Exactly as you said, we'll just make the delta x small, right? Great, yeah, it's going to get better. We definitely know that. But the computation is also just going to increase, right? So instead, where should I make delta x small and where should I make it big, right? Very good point. When to stop the computation, because as we said, you shrink it to, 0, it's fine. 0 is very, very small and means a lot of boxes, right? So when do I know I have this uncertainty of my integral? How many more, if I make the boxes half the size, how much better am I going to get, right? So I can get a stopping criteria. And then, as we said again, the effect from downstream tasks is I have this uncertainty, so I have the data, the model, and the computation. Now my predictions that goes into the next task, I can make a sensible decision from that. So people have thought about this a long time ago. So Poincaré wrote this nice, beautiful stuff, right? But then it really starts coming up when we get computers, right? And before we had massive computers that had like 96 bits floating points you had your 8-bit fixed point floats instead, so you got enormous amount of rounding errors everywhere. Well, Neumann said this thing, so rounding errors are strictly very complicated, but uniquely defined number theoretical functions of the inputs. Yet our ignorance of their true nature is such that we best treat them as random variables. So in this case, it's just something here that, cool, this is a completely deterministic system, but it takes me an awful amount of effort to trace all these deterministic computations. So maybe it's just better to see them statistically. So I actually do this for speed instead. Okay? So the notion very often is that as soon as we get uncertainties, as soon as we start working with Bayesian methods, you're slower. That's definitely not true in this case. Right? Okay, that's one of the benefits, the potential benefits. So I've also wanted to mention, before I go into the details, is two other people who really revolutionized this field. So Albert Soldin, who was at the university in Kazan, who I believe is in Siberia, wrote lots of stuff in Soviet Union journals that no one knew about. So what he worked on was error minimizing estimated numerical algorithms. And effectively what this led to was to how do you design algorithms from a statistical perspective. Lots of really cool stuff there. And then in the UK and later in the US, Fred Larkin, who was looking at the notion that we talked about, how can I incorporate prior knowledge of what I'm computing into numerical algorithms? And he thought about this from a robustness perspective. Cool. So what we're going to do now then is that we're going to walk through an example of how we can use exactly the things that we've done in this framework, and we're specifically going to do quadrature rules, so exactly those boxes to compute integrals. But it's just an example of thinking about this. So we're going to take this function, which is the one I've plotted, so f of x here, so the integral, fully specified, deterministic. It will take you whatever the smallest time thing you go in a computer to compute each one of these. So the integral itself, the value of it, is also a deterministic value. We know that. However, we can't compute this one analytically, right? We know a lot about it though. So I know that it's bounded everywhere by e minus x squared. It's bounded everywhere. This function I can integrate, square root of pi. I think, good, thank you. And so I also know the function is positive everywhere. So I know a lot about this function, and it would feel silly if I threw that stuff away. Right? So, what would I ideally want? Ideally, I would want this distribution, right? So I would want the conditional distribution of the integral value given the observations that I'm taking. If I have this distribution, I have an objective that I can follow, right? I can say that I want to pick x locations that will lead me to minimizing the variance of this thing, right? Cool. I would also have the uncertainty of what I currently have. So I can keep that on and say, you know, I'm pretty dead certain now, so stop doing the computation, right? So if I have this object, this here would allow me to do the active learning loop that we did before. So how do we do this? Well, we're going to do it in exactly the same way as we did here before. We're going to do emulation, right? So we are going to put an emulator on top of this function. And in this case, I'm going to do the simplest thing. I'm not even going to incorporate all the knowledge that I have. I just want to show you this example. So I have this function that we want to integrate. I now set the prior, and I'm sampling from this prior, and I'm computing the integral. And then we're seeing the distribution of these things here, right? Cool. So in the beginning, these are the values of the histograms of these. Now I'm seeing some data points. I'm seeing this being altered, seeing some more data points, right? Not very unexpected, right? So I use curve at each point, use fitted, I take the GP posterior, I sample from it, that's the diversity, that's the uncertainty I got left, and I compute the integral for it, and if I got all that many points, well, they're all the same, effectively, right? Now, the way we want to do this is that we want to be clever so that we can hit points in a much more clever way. Yep.
Don't we also have here the uncertainty when we're like computing the integrals over these Gaussian processes?
Ah, you might think so, but we don't. You can actually do this, depend on the covariance function. I'll show you exactly how to do that. So you can do that in closed form if it is, because it's a linear operator, right? So you can actually do this. So it becomes integrals over the covariance function. So the question is if you can compute the integral of the covariance function itself. Awesome. Very good. So effectively, what we want to do is, again, we take the comparison that we had before, right? Where I said, you know, I came back to this plot. Sure, I can compute this by grabbing all the possible data that we have, and I'm going to get a really good estimate. The only thing I might have to say is that the function is bounded or something silly like that, right? Or I can use very few data points if I incorporate all my knowledge, right? And that's a trade-off we've always been playing, right? But now we're adding costs, right? And in this case, the cost is really directly associated with the data. Yeah. Cool. So what we're going to do is that we're going to follow a formulation that was, I think, first written in a paper by Tony O'Hagan, who is a statistician who's known emeritus, I believe, up in Sheffield. Tony did an enormous amount of work that was way ahead of its time, that people just keep rediscovering. This paper itself is an absolute, it's fantastic. Hopefully I do a good job of presenting it, but given how good this paper is, you can go off and read it. It's very short and it's written in a beautiful story manner. The references are in the end of the slides. So what Tony is saying is this. So what I have is that I want the joint distribution of the integral and the observed values of the function y. Okay? So I'm going to incorporate the knowledge that I have of the function in a distribution here. Notice the price is going to be a Gaussian process. Then I have a likelihood function, the same as before, saying this is the function value. What do I think the discrepancy is to the data that I see? And then we have another distribution that says, if I know what the function is, what is its integral? Okay. Now we're going to simplify this a lot. We're going to pick delta functions for both of these two distributions. So what this says, the first one's not very surprising. If I know what the function is, I know what the integral is. So as long as all my functions are computable, that I can compute the integral of them, hope you believe this, right? It just says there's no discrepancy between the analytical solution and whatever the integral is. Right? So it's just the delta function. And then we say there's no noise whatsoever in this function. We're observing the correct noise. So we just have a delta function here as well. Great. So if we write this up, this is exactly how it looks like. So on the top row, the top bit, so the distribution over y, is just a normal Gaussian process, right? So I've got some mean function, and then I have some covariance function. And then all the other terms, right, are just computations of that delta function. So it says, now I pick a function and I integrate it. Now, the integration is a linear operator. Gaussians are closed under linearity, so it stays a Gaussian. So this here is actually a joint Gaussian distribution over the data that I see and the integral. The bottom one there, right, is a one-dimensional thing, right? It's just the value. The y's are all the things I see. Now, if this is just the joint Gaussian, the distribution that we wanted to have before was the conditional. You know how to condition a Gaussian, right? It's the exact same procedure as we did with the predicted distribution, with the linear regression. We've done this lots of times now, right? So actually, what I can do is I can get that out and it's just to give me the area of Gaussian. Cool. So then this would allow us to think about these information operators, acquisition function. In quadrature, people often call these design rules, right? So what you would normally think of makes sense is to reduce the variance of that integral itself, right? Which would be something like that. Now, you have an acquisition function, you can go out and do exactly what we did before, right? Cool? Simple as that. So, knowing that this stuff works out this way, I've hidden a little bit from you here. It's not rocket science, but that's not the point that I want to get across, right? Cool. So, let me then show you the next benefit. If you hope you agree with this, right? If I have this distribution, I can be a lot more clever where I pick the points, right? So, let's take this covariance function. Okay, this is a Wiener process, which is this covariance function, like it odd one. So it's a piecewise linear function. It looks like this. This is samples for this. Okay. What I'm going to do now is that I'm going to apply exactly the integral that we had before. And then I'm going to show you what the mean of the integral value is. Okay? So the expected value of the integral. Okay? So I take that, take exactly the formulation before the Gaussian process and all these things, and then I compute the expected value. So I take the predicted distribution that I learned from the GP, and I integrate that. This here is the expected value of the integral. So I pick out that model. That is the value of that. Have you seen this before?
Here is the rule you showed us.
It's a trapezoid rule, right? So now that's very cool, actually. So why is this cool? Now I get very excited when I see this, which may mean I'm a very tragic person, but I'm going to try and make you feel excited about this as well, right? So it's the normal trapezoid rule that's been around forever, right? This is like the natural way to compute an integral. It was derived in a completely different way, right? It was derived by making an assumption about the function. Not rocket science, right? I made the assumption that the function is piecewise linear, and I end up with a trapezoid rule. Yeah, it kind of makes sense, right? But think now about placing different assumptions on the function will lead you to different algorithms, right? So, yeah, that's the thing we've shown before. So, if we want to then redefine what the trapezoid rule is, we can see what it actually is. We can think about it like this. The trapezoidal rule is the posterior mean estimate for the integral under any centered linear process that has this covariance function. Right? Now we have a definition of when the trapezoid rule should be used and where it comes from. Right? Before, it was just an algorithm and someone picked out of their hat because it kind of makes sense. Now it's tied to what we're solving. Right? This is very, very, very cool because this allows you to do lots of interesting analysis. Right? Effectively, I'm coming to you in a second. Effectively, right? We have this thing, right? When we talked about, we wanted to think about the scientific principle. If something works, does well on something, it's somehow evidence of supporting our hypothesis, right? So if I take lots of different algorithms, I know this algorithm works really well on these types of functions. If it works well, it now says something about the function. If I don't know the assumptions that I made of that algorithm, I can't do this, right? Yes.
How is the covariance function we saw earlier even a valid covariance function? If kappa is positive and the variance can be negative.
Yes, exactly. So the value of there is a few constraints on both theta and kappa in that one for it to be a valid covariance function. Yeah. So I dropped them from my definition, but those things, yeah, it has to be a valid covariance function, right? And they're not valid for all of them. I think theta is just the real values, but then kappa can't make it negative, right, on the diagonal. Yeah, cool. So if I want to draw this to an even further extent, right? So you remember least square regression, right? There was this fight, or people talk about Lagrange or Gauss, right? One of them was an algorithm that produces some error. Gauss' method was saying, if I make this assumption, this is the algorithm that you should use, right? This provides you with a whole different way of thinking about the problem. And an even better example, I think, is this. If you think of the original paper of factor analysis, 1904 from Spearman, proposed this thing that was completely ill-proposed, proposed the solution to this. And the notion of this was to extract factors in experimental psychology. This paper, if you want to read this paper, it's a really, really scary paper because it's basically eugenics, right? It's horrible. It's a complete misunderstanding. Maybe because they wanted it, but also because they didn't know what the assumptions this algorithm would do. Then you have Hotelling, which proposes the notion of PCA, where it's clearly defined through a statistical model. That says, if I assume this, then this happens. Right? And I think probabilistic numerics has a little bit of a similar notion with these things. So, if you then go, why would we do this? If you go to, for example, SciPy minimize, it has this variable called method. Here are the methods that at least last year when I generated the slides you can pick from. Each one of these methods work, but they give you different results on the same problem. That means, no free lunch, they're all implementing a different assumption. I have no idea, most of them are not formulated statistically, so I don't know which assumption they do. What I do know is that after many years of doing gradient-based optimization, I developed an instinct for which method I should use where. That's not very satisfactory. What I would want is something that says, if the function looks like this, you should probably use this method, right? That's what a statistical interpretation of this could lead to. So, tons of algorithms understand for every problem. Cool thing is, they work really well. We don't really use to understand why they work well because we don't have the statistical interpretation. So, what we would want to do, one, come up with what prior does these things implement, because then I can understand why they work. And more importantly, then I can design new algorithms, which is potentially really cool. So, just to wrap up, what I talked about today was use probabilistic numerics. The only thing you have to think about is we just extend exactly the same thing we've done for computation. That's it, really, right? Think about the evaluation as just an observation. So, computation is just the process of extracting a latent property. Machine learning is a statistical process of updating belief about latent properties. So therefore, we think about numerical algorithms just in the same sense. It gives us all the power of interpretability that comes from machine learning, and it gives us this notion of a decision support that can feed forward. Cool. So, just a couple of things. I just want to highlight this because I've said all these things before. But the notion is always when we do this kind of stuff, as soon as we parameterize our uncertainty, we're less efficient. Right? This does not necessarily need to be true in these cases, because you can be so much more clever of how you select what computations that you do, so the few computations that you do have much, much bigger value to what you're looking for, right? Okay. Cool. I am going to see if there's any questions on this. Yeah, to me, it's just the coolest thing since sliced bread. And just, yeah, last thing I wanted to hit. Why do I think this is so important now? So remember when I said, when we did statistical learning theory, and I said there's like 3 handles of any machine learning algorithm. It's your data set, it's your algorithm, and it's your model hypothesis space. We need to put in priors in these things. And then I said pretty much all the advances over the last 10 years, or 20 years probably now, or a substantial part of it, especially in the deep learning community, have come from one, cool, okay, big data, fine, right? But the other thing is inputting knowledge into the algorithm space, right? So finding out ways of searching solutions in a clever way. This here, how to do that, you learn by training algorithms for 5 years, and then you get an inductive knowledge of it. What would be really cool is these means, the stuff that we talked about, would actually be able to say statistically why these algorithms work, right? That would be a pipe dream, but that would be really, really cool. Right? Cool. I'm going to end there. I have more stuff, but I think this is probably a good time. So I just wanted to give you a flavor of these things, so you can see you can be uncertain about everything, even computation. Have we got any questions? Yeah.
So in every numerical algorithm, the supposedly statistically correct way to evaluate some prior?
Well, so every algorithm will have to make some assumption, right? In order. So say if you got, say if I have a function, I want to find its minima. This is what we were talking about in terms of base odds, right? We said, well, can you guarantee that you find the minima? No, I can't, right? What I can do if I assume some form of smoothness of the function, I can now say that's one assumption, right? And if they have a statistical interpretation, I think they should have, it's just a different narrative of that. So the question is just if we can extract it, right? Cool, more questions? Okay. So I'm just going to end with then, if you enjoy this stuff, we're running an R255 unit on exactly this. I'm not doing much in R255, you guys are, but if you want to take that, we're going to do pretty much this stuff, but figuring out specific algorithms, right? This was more just of a teaser of something that I think is really exciting. Yeah, cool. Thank you very much.
Can I ask about the upcoming assignment, please?
Yeah.
So I couldn't find anything on Google or
It's hang on. Do you want stop cloud recording? Yeah, let me just say that. Yes.